Activate brain.
All right.
Okay, since the blue is a square,
Andrew, breathe first. Breathe first. It's okay. I'm excited about math too.
Alright. Since the blue is a confirmed square by you, then that means that every angle should be 90 degrees.
Correct.
And since that's a confirmed rectangle, every angle should be 90 degrees.
Yep.
So that leads us closer to our investigation.
Yes.
Big brain.
What else you got for me?
Like,
Katie.
Okay, I don't know if this.
That's fine.
Okay, I don't think it can work, but so you know how you have like the midpoint thingy, and then like that side is like half of like the other side. Can you do that like on the other sides? Like I don't.
So you want to get that here?
Yeah.
There should be a way to divide that up. The problem is I don't know if that's a third or not.
Okay.
Does that make sense? Right? Maybe that's a third and that's a third and that's a third, right?
Okay.
I don't know where those dots go. But good point, because we can figure that out, then we kind of win. Mark.
Wouldn't so like on the big square, like wouldn't like the side with the two, like wouldn't the side with the midpoint be like proportional to like the other side? So like there's like
There's a 2-to-1 proportionality there. Now, remember, triangles can have relationships, right? All numbers do. So to have two triangles that have sides like that, right? One's half of the other, is not shocking, right? Does that mean the triangles are similar? No, one side is not enough, and here's why. Because this could be 3 and that could be 7, and this could be 8 and that could be 22, right? So you're on to something. Maybe they will end up being similar, and if they have a similarity, right, we can say that they're proportional by 2. That'd be great, but it could also be this, right? So if you can prove those triangles similar, or congruent, then that would be good. Then we could say that this is 2 and that's 1, which means this would be 2 and that's 1, right? Something like that. Cool. Yeah, that sounds like a winning strategy. How can we get these triangles similar?
hey Mac, question.
Hold on 1 second. Katie?
Okay, well we have an angle and a side already, so if we got like another side, would that work?
Side angle, side similarity. Yep, you can do that. If you knew that this is proportional to this by 2 to 1, and this is 2 to 1, then yes, they would be similar. But the problem with that is, if we have those sides, then we've already won, right? So we're not going to get that. Yeah.
So we know that there's a shared side and a shared angle between the two from the bottom right
Not
and
shared,
top
congruent, right?
Congruent,
So
yeah.
you're saying these two are congruent, these two
Yeah.
are congruent? Okay, cool.
So wouldn't that make the two of the shared angle, the two congruent sides, congruent to the one on the top right? Would that help us any?
Not congruent, maybe similar, but we don't have enough information to do that. Remember, we need double angle, or we need side angle sides proportionality, or we need side proportionality. Right now we have the side and angle. If we had 2 angles, we could. Yeah, Mark.
So since like the red rectangle is like touching like the big square, could we like make angles out of it, like on both sides?
We could, like here and here,
Yeah,
right?
yeah.
Wouldn't that all add up to 180? That's
Yeah.
true. So we can figure out that angle, we get that angle, right?
And
That's true.
And then we'd have like 2 angles, and then we could use AA similarity.
That's very right. Question is, how do we get those angles, right?
Yeah, I forgot the name of like.
Yeah. Well, we can't use vertical here, right? It's not an X, right? It's like a K, so vertical doesn't work. But if we knew one of them, we get the other one by linear pair, right? Or by angle addition, right? What do you know about rectangles?
One side's bigger than the other, or longer.
Sure, but lots of shapes have one side bigger than the other.
And squares.
Squares don't have one side bigger than the other. What you're saying, I think, is you're hearing what you're saying is not good enough for what you actually mean. Yeah.
The lines are parallel.
That's also true, yep. These will be parallel, right, because they're both 90, right? So we have 2 lines with the same angle and a transversal, which means by corresponding angles postulate, right? Converse, then these would be parallel. That's true. I'll draw that in. These guys are parallel. And these guys are parallel. I love that you guys see that. And then, of course, this would be parallel to this, because squares do the same thing, and this would be parallel. this. Ooh, whoops.
Since they're parallel, does that mean that we could extend the lines?
We could. Now, you guys are thinking way too big brain here. What do you know about rectangles? This is all true stuff.
Length times width equals.
Marissa, you have your hand up?
Yeah. So are we like trying to find a number for the area, or is it like a?
Now, that's a great point. Will we be able to find a number for the area? No. How do you know this?
No numbers.
We don't know how big anything is, right? If the square were bigger, wouldn't the area of this rectangle be bigger, right? And if the square is smaller, then the area would be smaller. There's a relationship that we're going to find. So one thing you might do is you might say, look, I know this whole square is x by x, according to me, right? And then you'd be able to find the area as some kind of value of x, right? Now it depends on what x is, right, for the area to actually be for a number, right? But if we don't mind getting a formula, right, we can get a formula using x. Yeah.
So, like the area is gonna be, is it gonna be like a relationship, or is like the
Yeah.
x formula?
It's going to be like a proportion, or yeah, it's going to be something like that.
Mac, if we know that the bottom left triangle and the top right triangle are the same size, can we combine those together since they're right triangles to make a square?
You could, that is true.
That help us anyway.
But we don't know that they're congruent yet, right? That's the question I'm asking. How do we get these congruent or similar? What do you know about rectangles? Come on. You got plenty of information about squares. Quinn sort of said
They're
it.
very long squares.
Squares and rectangles?
Yeah, what's the difference between a square and a rectangle?
Side lengths.
Yeah. Aren't opposite sides always congruent for a rectangle? Right? But not necessarily all sides? Right? So these two sides will be congruent, and these two sides will be congruent. Right? So what you said was true, Quinn.
Okay.
But it's the opposite sides that are the same. Yeah, we have different sides. Yeah, lots of things have different sides. The point is what's the same, right? Opposite sides are the same. So now, still can't prove that these guys are proportional necessarily, right? This is 2 to 1, but do we know that this is 2 to 1? Not necessarily, right? We don't. It'd be 4 to 1 or something, right? But we do know something about these two triangles. What do we have here? Ass. But the right triangle, so that means by HL they're congruent, right? You guys see HL, hypotenuse leg? So this triangle is congruent to this triangle. What else do you see?
Are we able to prove that the two larger triangles are congruent?
How would you do it?
The SAS.
Not SAS.
Oh,
ASS, right? ASS. But it's 90, so we can use HL, right? So HL. So now we have a bunch of congruent triangles. Aren't congruent triangles, aren't they always similar?
yes.
They're related by a 1-to-1 ratio, right? Not double, they're not half. They're always similar. And the way you can prove that is very easily. If congruent triangles are congruent, then they have congruent parts, right? So whatever this angle is right here, shouldn't that be the same as this guy down here? Right, they're congruent. They should have corresponding parts. How do I know those parts go together? That angle's made up of the 2 side and the 3 side. I go down here, 2 side and 3 side, those angles are the same, right? Same thing here. This angle and this angle should be congruent because those triangles are congruent now, right? And then Mark, this is where you take over from what you were saying earlier. What else do we know? Here. You should all add up to 180, right? So that angle should be the same as this angle, right? Pink, red, what's left over should all add up to 180. So they're the same. Now, before I color them in, we already know what value that'll be, what color that should be. It's a color that's already on here. It's purple. And you know how I know that? 180 minus red minus
Corresponding
pink
angles postulated.
gets me this, right? 180 minus red minus pink gets me that, doesn't it? Right? 180 for triangles, internal angles, 180 for linear pair. There's always a connection that you guys should look to exploit, right? If these add up to 180, and these add up to 180, that leftover bit must be purple. So this is purple, and this is purple, purple, red, and pink all make 180. So if I already know I've got red and pink, then purple must be the last piece. Same thing here, but with pink, right? Purple, red, and pink all go together to make 180, according to these triangles. So now we've got a bunch of similar triangles. And congruent, but similar is going to be most useful here, right? Relating these guys. And if they're similar, if this is 2 to 1, what should this side be? 2 to 1, right? And if these are 2 to 1, and they're similar, then this should be 2 to 1. So whatever this is double it. And whatever this is double it. I'm going to leave this for you guys. For now, you guys did an excellent job with this. See if you can finish it up for self-development. Figure out what we have to do to find the area, right? We'll come back to it. Do it on your own. Or work together, but just not with me. All right, nice job.
Or you have to prove that there are 2 to 1 ratios
Period 4.
between those.
This is period 1, I think. Period 1 did some similar stuff.
Huh?
All right, let's take a look at this thing. Buckle up, we've got a lot to get through. We are not grading your quiz today, because here's my opinion on this. I think most of you guys did pretty poorly because you didn't take my warning seriously. And those of you that did just needed more time to process and have that sunk in your mind instead of it be a bunch of stuff you have to memorize, right? You need to see the concepts. If you want to come see me for help about that, that'd be great. Here's what we're going to do. Nice shoes, isn't it?
I got them for Christmas.
Really nice. Instead of grading it today, I'm going to grade it Wednesday because we have an early out. And I figured that'd be a better use of our time. I'm still trying to get used to how the school works, the structure of my class, right? My beginning of the year is like, oh, we're quiz every Friday, right? Obviously that doesn't happen anymore, right? It changes with how the school works. We have so many days off because of how the school's structured. It just kind of throws that system off. I think it'd be a better use of our time to spend Wednesday grading it than today, which means, in theory, you could say, I didn't finish my quiz, which you all should have because there's plenty of time to do it. And you can go back and fix it without it being retaken. So before you come see me, okay, make sure you study up, really understand this stuff. Okay, ask questions. Don't ask questions right before you retake it, or you pull it out of the bin and finish it, right? Figure it out. Work together. Some of you did really well, and some of you did really poorly. It's the difference between seeing the connections and just trying to memorize random crap. If it's just random crap, it's hard to memorize it. But if you see the connections, it's no longer random crap, and it's easy to memorize, right? Because it all is connected. So, just like M&M, you're going to get one shot. Take it, just let it slip. You get one. So don't come to me today and be like, I'll try it for 10 minutes after school, and I'll come back on Tuesday and do it 10 minutes. We're not doing that, right? Because then you just go home and study the ones you know now. Now, all y'all thought the quiz was done, and so over the weekend you didn't think about it and don't even memorize what problems or questions are on there. Which means I think it's fair to let you guys continue. Because no one went home and really took advantage of it. Not that you would have anyway, you're all too big being dummies, right? But I think it's fair to do it in this case. It's all out. But you get one shot. You can't come in 3 days and be like, I'll just piece it together. We're not doing that crap, okay? Just gotta know your crap. You know that. All right, so here we are. Continuing with last week. Now, see, last week, don't be scared, it's fine. Last week, we talked about a bunch of different types of segments and triangles, right? And we assumed very well, right? Basically a postulate. We messed around with GeoGebra, and we did all the angle bisectors, and we saw they always intersected at a point. No matter what I did to the triangle, they still always were concurrent, right? They always intersected at one point. We had something like this, right? All 3 lines would always do this, which is pretty rare, right? Because 3 random lines aren't going to be concurrent, right? But it always seemed to work that way when we had a triangle. We said the angle bisectors would always be concurrent. We said perpendicular bisectors of the triangle will always be concurrent. We said medians will always be concurrent. We said orthogonals will always be concurrent. And we didn't prove that, but we assumed it to be true because when we went to GeoGebra, moved the triangle around all over, they were always concurrent, right? They never split apart. They never ended up looking like this. They were always intersecting at one point, right? We assumed that. This week we're going to prove it. In order to do that, it's going to take a little bit. Before I can even get to the proof, I need you to understand some stuffs about algebra and some stuffs about triangles that we have not talked about before. So what we have is our first lemma. a lemma is something that before a proof you need your audience to understand. It's like, look, before I can even get to explaining this thing, I need you to understand this basic concept, so when I use it, you won't freak out, right? Now, we've done this in class all the time, I just haven't called it a lemma. Been like, look, let's draw some example triangles, let's talk about it, right? You know, we do that all the time. Here is something that's not quite so obvious, and so I want to call it formally a lemma to my proof. In fact, we're going to have two lemmas before I can get into the proof. We're going to prove this. That way when you see I have this and I say, that means I get this, you aren't going to go, wait, what? How? And that a triangle, the area of that triangle is always proportional to its base and height. Now again, you know this formula, area is base times height divided by 2 times a half, right? But the fact that the proportional might seem a little bit weird. It shouldn't, but I want to make sure you're good to go. So I'm going to establish those two things. And then we're going to prove Ceva's theorem, which is this. Okay? And this will apply to all of the things we worked on last week, more or less. And it'll prove concurrency. So, step one, I need to convince you that if this is true, then that's always true. Okay? And you're like, wait, what? Okay, pause. All this means is that we have a bunch of proportions, right? We have things that are proportional. We've done that with sides of a triangle, right, for similarity, right? We've done with that, right? I just use little letters. If I use numbers, I think it becomes a little more clear what this is saying. Pick a number for A. Let's just show it with numbers. Give me a number for A.
2.
2, okay. Mark, give me an even number for B.
6.
Okay. All right. So if this, what we mean is, for example, 2 divided by 6, right? What could I write here? Now I could write 2 divided by 6 for all of these, right? They'd all be equal. Well, what's another thing I could write here that isn't 2 divided by 6? Yeah, Mark?
1 over 3.
1 over 3. Right? Do you see how 2 over 6 reduces to 1/3? Right? So they're equivalent. What's another thing I could write here? Yeah.
3 over 9.
3 over 9. Now, they're all different numbers. They could have all been the same, right? That would have been boring. But I made all different numbers, A, B, C, D, E, F. If this is true, then you should be able to take these numbers and move here. Now again, let's talk about proportionality. Why do we even use a division sign to show relationships, right? Why is that a thing? 6 and 2, how do they relate? How do 6 and 2 relate? What's the relationship between 6 and 2?
3.
Times 3, right? Or if you're going the other way, times a third, right? Cut into thirds. If you do a division bar between 6 and 2, doesn't it show you the relationship? Right, now you know the relationship between 6 and 2. It's times 3, right? Of course, right? I don't need to do that. Why would I need to do that? What's the relationship between 7 and 3?
4.
I mean, that's the difference, right? What's the relationship? 3 times what is 7? 7 times what is 3? Either way, I don't care which way you do it. 6 times 3 is 2. 2 divided by 3 is 6, right? Whichever way you want to do it is fine. But 7 and 3, what's the relationship? You don't know.
2.
It's 7/3. That's the relationship. 7 is 7/3 of 3. Is that weird? 3 is 3/3 of 7. Is that better? 3 is 3/3 of 7, right?
I gotta move it up.
Oh no. 3 is 3/3 of 7. Right? Isn't 2 2/4 of 4? Right? Isn't 1 half of 2? Isn't 3 3/6 of 6? Right? When we show division, it shows the relationship, right? 7 and 3 relate by 7/3. That's how they relate. 7 is 7/3 of 7 is 7/3 of 3. Okay. How do 2 and 6 relate? How do 1 and 3 relate? How do 3 and 9 relate? They all relate by a third. Right? So we're saying if these are all equal, you should be able to take these numbers and do this. Okay. So let's do that. We said A was 2, and C was 1, and B was 6, and D was 3. And that should equal E over F, E over I. Now with numbers, I think you'll agree, this checks out, right? Now this only works if the number is equal to 4. You can't just take random fractions and subtract them, and that's not even how we subtract fractions, right? We gotta get common denominators, right? The point is that they're all the same fraction. You can do this. Now, this isn't very useful or interesting with numbers, but if I were to tell you the sides of these triangles are proportional, and then show you that, you'd be like, wait, what? Right? And that's what we're gonna do. So first I'm gonna show you that this is true. Not just for this set of numbers, but for all numbers. Now, before I start this proof, that this means that, I need to figure out what I'm even trying to accomplish. Like, how do I even get from that to this? Right, I've got 2 equal signs here, 1 equal sign there. What am I even doing? Here's what I'm gonna do. You guys remember when we proved Pythagorean theorem? Right, we had to get a squared equals something and b squared equals something, and then we added them together and then move stuff around, right? So I'm gonna get a and c on their own. And the reason I know to do that is this. Take a look at this top part right here. I'm gonna mess with it to kind of show you why I know I need to get a and c on its own. Isn't that divides by b minus d, right? How do I undo divides by something? Multiply. So I can multiply by b minus d. I'm treating that as a whole number, right? If that was divides by 2, you know what to do, right? Times by 2, right? I'm going to treat that as a whole number and times it over. And so when I do that, I have to wrap in parentheses because it's being treated as a whole number. We cool with that? I just moved it all over by its multiplication. We cool with that? Now, we multiply to the top and divide to the bottom, right? So I'm multiplying by b minus d, so I put it in the top. Cool. And then I'm going to distribute the e. So I think you can see what I'm saying. If I know what a and c are, I can take those things, instead of adding them like we did for Pythagorean theorem, right? A squared and b squared, right? And then seeing what happens, right? I'm going to find out what a and c are. Then I'm going to subtract them and see what happens. I'm going to mess with stuff and get this. Then we'll work backwards to get to here. Okay? So I'm going to get a and c on their own from here. Find out what they equal, right? And I'm going to plug them in, do a minus c, and then see what happens. And it's going to look something like this. And I'll work myself backwards to here. Okay? So here we go. Starting with what they gave us. So I want to know what a equals. Well, a equals a bunch of things. It equals b times c over d. It equals b times e over f, right? I want f on the bottom, right? So let's see what a equals with this guy, right? I'm going to take these two. I'm going to do the same thing for c. Right, so far, not blowing anybody's mind, right? That equals that, that equals that. I'm going to get a on its own. I'll get c on its own. Now I know what a and c are. Okay. So if I know what a is, I know what c is. What is a minus c? Well, a is this. And c is this. You see where I'm going here? Don't they have common denominators? They do, right? They're all over f. How many f's were given? B over e, or be, and de. That many f's. We're going to subtract them and we're going to get something over f, okay? What's up?
That's the joke.
Yeah, go ahead. Now we're here. I pulled out an E from both of those guys and put it out front, right? You cool with that? If I were to go backwards, I would get EB minus ED. Same thing. Okay. And then I'm going to move that over by division. I'm going to divide that out. If that's weird to you, I can rewrite this like this. Right, you guys see that? Multiplication in the top here, right? It's E divided by F times B minus D. Same thing here. We cool with that? And then I divide by B minus D. Ta-da! It's true. Move stuff around to get A and C on their own. Subtract them, right? See what happens. You get this. So if all these are equal, this is true. You're allowed to do this to any numbers. For example, like we did before. Give me some equivalent fractions. Give me 3 equivalent fractions. What's equivalent to 5 over 15? 1/3 and?
3/9.
And if I do that, I should be allowed to do this, right? Very weird, only works with equivalent fractions. And I get 4 over 12. It's 4 over 12, 3/9. So what happened? Hello?
Simplify them.
Yeah, you simplify them, right? That's a third, and that's a third. We're good. Right? So as long as you have equivalent fractions, you can subtract 2 in a very weird way, right? You don't even common denominators, you know, you get the third one. Okay? So if 3 things are proportional, we can say this. Okay? Kind of weird, but it's true. All I did was take this, find out what A and C are, and I subtracted them, and what I got gave me this. Okay? So that is a true thing. So if I have something like this, I can jump to that. We go with that. Turn the page. The area of a triangle is proportional to its base and its height. I don't think anyone will be shocked if I write area of a triangle equals base times height divided by 2, right? We go with that? Well, the area of a triangle divided by its height equals half its base. What? How'd I get that? How'd I get that? What did I do?
You separated the H.
Yeah.
Because you divided. Yeah.
Multiplication happens at the top, right? So I divide by h and it's over here now. Right? So if you take the area of a triangle and divide it by its height, you get the base divided by 2. Half of its base, right? I can do that switching these. Right? Let's talk about this triangle. How many triangles do you see? 3! 1, 2, and 3. Let's label them. Let's call it blue triangle, green triangle, and the triangle we don't care about. Alright, so we have 3 triangles. I'm only talking about these 2. The area of the blue triangle would be half. What's the base of this guy? C, little c. Base times its height. What's its height? Looks like that's its height, right? So h. Cool. The area of the green triangle would be half. Its base, what's its base? Blue one has little c. Green one has what? Little d. Now what's the height of this one? We can't call it h unless it's the same, right? What's the height of this one? It's also h, isn't it? These 2 triangles have the same height. From here to here is the height, right? And from here all the way up to there is the height. It's the same. Do you see it? If 2 triangles are inside another one, their heights are always the same. Look, that's the height of this guy. That's also the height of this guy. They're the same height. This guy's height goes from here to here. Right? To the top. And this guy's height goes from here to here. They're the same height. So that's true. Now this only works if their heights are the same. When you compare the area of those triangles, right, try to figure out their relationship, try to figure out their proportion, right? How do they relate? How do the areas of these two triangles relate? You know, if this is 6, is that 3, right? How does the area of these triangles relate? Well, when they have the same height, this is how they relate. They relate to their bases. And I'll show you why. That's how the area of two triangles relate, right? Now, what's special about these triangles? They have the same height, right? What's a half divided by a half?
1/4.
Nope. That's times a half. Any number divided by itself is, nope. Any number divided by itself is 1. Yep. So what's a half divided by a half? It's 1, right? Thank you. And since h's are the same, what's h divided by h?
1.
Again, if their heights weren't the same, we couldn't do that, right? We'd have different heights, but they're the same height, so they're 1. So multiplication, right? Doesn't go away, right? Becomes 1. What's 1 times c times 1? I swear. C. Bueno. So the area of the blue triangle and the area of the green triangle, how do they relate? The same way their bases do. What does this mean? If I told you this area was 6, and I told you this area was 2, what's the relationship of the areas here? 3, 6 divided by 2, right? So the relationship of the areas in this triangle would be 3. That should be the same relationship as the sides, the bases. So if I knew this base down here was, I don't know, let's do 10. No, let's do a better number. Let's pick 30. 6 to 2 is a third, right? We know that the area should relate to its bases as long as the heights are the same, right? So 6 relates to 2 the same way 30 relates to 10. So if you knew this, area of 6, area of 2, base of 30, because they have the same height, you know that has to be the base of 10. They're all 1/3. The area of triangles with same heights will be proportional to the bases. The area relates the same way that the bases do. We cool with that? So if this was times 4, this would be times 4. If this was times a half, this would be times a half. Now this is only true when the heights are the same, right? Because otherwise the heights don't become 1 over here, right? They'd still be down here. But when the heights are the same, the areas relate the same way that their bases do. Okay? Those are our two lemmas. Triangles of the same height, their areas relate the same way their bases do. This means this. You can do that. That's fine. You can also add if you want. Notice that this was a plus here. We get 3 and 9, and that's equal to 3 ninths, right? So you can add or subtract, and that'll be true. I want subtraction because that's the one we're going to end up using. I got one last thing for you. It's not a lemma. It's a definition. Page 3. Cevians. It's any segment that connects a vertex of a triangle to its opposite side towards your arc. Okay. So what does that mean? Let's draw an example. It's a triangle. Why do we call it a triangle? Because it has 3 angles. Nice job. And those angles have vertices, right? A vertex. If I draw a line from the vertex to the opposite side, anywhere, that line is a Cevian. Any of these would be Cevians that I could draw. Do we know that that Cevian cuts it in half on the other side? No. Do we know that it hits it at 90? No. Do we know that it cuts this angle in half? No. But we know that it's vertex to the opposite side, so we win. Now this also counts if I were to extend this side. If I drew from vertex to here, that would also be a Cevian. Would they be congruent? No, I'm not saying that. I'm just saying, look, those are Cevians. They're anywhere from vertex to opposite side, okay? And that opposite side can be extended to make that count. You cool with that? Now we've learned about cVians before, but we learned about specific kinds of cVians. So here are the types of cVians you know already. They're like cVians, but more specific. The angle bisectors of a triangle are cVians. Right? Here's a triangle. Here's an angle bisector. How do I know that's an angle bisector? Because it bisects the angle, right? Is that a cVian? Vertex to opposite side? Oh yeah. Now it's a cVian that we know more about, right? It's a specific kind of cVian, an angle bisector, but it's still cVian. Okay? cVian's the general term. What other cVians do we know about?
Is that
Median will be, won't it? Because medians are what to what? Vertex to midpoint. Nice job. So this will be a cVian, right? Vertex to midpoint. That's vertex to opposite sides, right? We got one more.
Isn't there perpendicular?
There's a perpendicular one, yep. What's the word we use? Starts with an O?
Orthogonal?
That's right. Orthogonals will also be cVians. Now you might be thinking, wait a minute, we had 4 centers last week, and I'll explain. An orthogonal, that just means it goes from the vertex to the opposite side at 90, right? So again, all are cVians. They're just specific kinds of cVians. This one hits at 90, this one divides the side in half, and this one divides the angle in half, right? They're just cVians with a different purpose, right? Now you might be thinking, wait a minute, what about perpendicular bisectors? Here's your problem. Easy problem.
I have no problem.
cVian or no?
no.
No.
cVian or no? It is. It's a secret cVian. Because if you extend the sides, it works. Remember, orthogonals can go outside too, right? It's okay. If you extend the sides, it goes to the opposite side, right? Right? What's the opposite side of this side? This side, right? Already goes there. Wait a minute, something's wrong. What's the definition of cVian?
The thingy thing.
Any second recognize vertex.
Vertex to what? The opposite side. Well, it hits the opposite side. That's the opposite side. That's not even the opposite side. But does it go from vertex to opposite side? No, it doesn't, so it doesn't count. Sometimes they don't. Sometimes they end up being that way, like if that bisected as well, be a perpendicular bisector, and be like, oh yeah, it's a cVian, great. But most perpendicular bisectors for triangle won't be, right? They'll go off at a random angle. Not really random, but they'll, you know, they don't go to the vertex. So, now you know what a cVian is. Behold! Name some cVians in this triangle.
BF.
BF, DC, and AE are all cVians. And not only are they cVians, but this says they're concurrent. And if they're concurrent, then this should be true. Are you seeing this? Macy, I know you're not. This will be true. The relationship between A and B times the relationship of C and D times the relationship of E and F will be 1. Their relationship times their relationship times their relationship will be 1. And this is only true if this is concurrent. And it works for any type of cVian. It works for bisectors of the angle or of the opposite side. Works on orthogonal. It doesn't work on perpendicular bisectors, but if they're concurrent and they're cVians, then this will be true. Now we're going to use the converse of this theorem to prove concurrency. We're going to say, if this is true, then those guys must be concurrent. But first we're going to prove the theorem, okay? Turn the page. Let's prove it. Remember our 2 lemmas. We have the triangle thing, right? If the heights are the same, then their areas relate the same way as the bases, right? And then we have that weird thing where A over B equals C over D equals D over F, and we get A minus C over B minus D equals D over F. Do you see any triangles in this diagram that have the same height? see it. What triangles have the same height in this diagram? What triangles have this height in this diagram? Well, the biggest one, right? But does it have a match? We can't compare it to. Yes. So check it out. ACD, gentlemen, ACD has the same height as BCD. So their areas should relate the same way as their bases do. A and B are going to be related, right? Now you might notice there's some other heights that are shared. I'll get there in a second. So the area of triangle ACD its relationship to this guy's area, BCD, is going to be the same as their bases, right? Remember that was our lemma? What's the base of ACD? What's its base? Little a. What's the base of BCD? Little b. What other triangles have those bases, A and B? These guys do, right? What other triangle has base A? Triangle what? What other triangle has base A? The big guy does. What other triangle? GAD. I'm going to call it ADG, okay, for alphabetical. It has base A, right? This triangle right here has base A. ADG has base A. What other triangle has base B? This triangle right here, right? BEG. We already did the one. All right.
Hey,
Nice
Matt.
job. See you tomorrow.
I guess you could call this a dilemma.
Yeah, she was 2 weeks ago.
Yes. A dilemma comes from the same idea, from the same word as lemma. Div meaning we don't have. Meaning if we don't have a lemma, we don't understand that there's a dilemma, there's an issue, right?
Jesus.
We require a lemma to understand.
Okay.
Bye.
Okay, Mr. Scientist. Jeez.